Okay, so for part one of homework 7-4, question one. And this question, hopefully not a bad one, it's kind of a trivial question from what we talked about in class, but a tire rolling around along a road, without slipping with a velocity of v. So when they define that velocity, they're talking about the velocity of the center of mass of that tire. A piece of tape is attached to the tire when the tape is opposite the road at the top of the tire. So when the tape is up here, what is its velocity with respect to the road? Well, again, this was the concept we talked about in class. As the tire rolls around, right, as it spins around, we know at the top it would be moving both linearly and rotationally, and both of those would be going in the same direction. So its velocity at the top would actually be twice as much as the linear velocity of the tire. So the correct answer for that is A there. So 2 times the linear velocity, right? The alternative to that would be at the bottom, right? At the bottom of the tire, the velocity and the linear velocity would be going opposite directions, and therefore it would be moving at 0 at the bottom. But again, this question is specifying at the top of the tire. So anyway, question one, like I said, once you know what that concept is, it's more of a trivial question, but a good one to make sure you're comfortable with. Question two says we have a uniform solid sphere with a radius r and a mass that is rolling without slipping. Again, the key there, if it's rolling without slipping, then it has both linear and rotational kinetic energy. Right, so I have both forms of that. It asks which form of kinetic energy is larger, right? So the key here is going to be we want to represent those in the same variables so that we can then compare which one's bigger. So what I mean by that is we know linear velocity is obviously just 1/2 mv squared, or right, linear kinetic energy, I should say, 1/2 mv squared. The rotational kinetic energy would be 1/2 I times omega squared, or keep in mind for a sphere, that would be 1/2 the moment of inertia for a sphere, which is 2/5 mr squared. And then if I break up the omega in terms of linear velocity, well, omega equals v over r. So if I break that up, then I've got v squared over r squared. So then obviously the r squareds can cancel out. And what this allows me to do is, again, make that comparison where I'm using the same variables. So 1/2 times 2/5 is 1/5. And then I have the mass of the object, which is the same mass, right? It's mass of the sphere. And then I have the linear velocity squared. So what this allows me to do is, again, this is representative of my rotational kinetic energy. And the first 1/2 mv squared is representative of my linear kinetic energy. So then all I have to do is compare which of those two is bigger. Well, obviously, if I just look at the coefficients, everything else is the same, right? They both have m and they both have v squared. So if I just look at my coefficients, it's hopefully very clear to see that 1/2 is bigger than 1/5, and therefore the linear kinetic energy would be much higher than the rotational kinetic energy. So option A, the translational kinetic energy, is larger than the rotational kinetic energy. Question 3 is really a very straightforward concept. It's just a quick concept check here. So the angular momentum of a system remains constant when which of the following is true? The total kinetic energy is constant. That is not true, right? Be careful with kinetic energy. Just like we saw for linear measurements, the kinetic energy is not always conserved in collisions, and therefore that is not the qualifying factor for this. When no net external forces act on the system, again, that one you have to be careful with because it sounds good, right? No net external force acts on the system. But in terms of angular momentum, the net external force isn't the issue. As long as there's no net torque, then it's not going to have a change in angular momentum. Right, so the external force does not necessarily assume that the system remains constant. Option C says when the linear momentum and energy are both constant. Again, not necessarily a qualifier here for that. And then finally, option D is the one that actually ends up being right. So when no torque acts on the system, and this really should say no net torque acts on the system here. But option D is going to be my best option, right? It is not always a conserved quantity, so option E is not right either. But option D, again, no net torque, that's what we're looking for. The angular momentum is conserved in times the net torque is 0. So question 4, question at this point in your physics careers you guys have seen asked a variety of different ways, but hopefully one that you are getting pretty comfortable with here. So they ask us which of these following objects would finish basically the race first, right? They're all dropped top the inclined plane, and they roll without slipping, so they do rotate. Which one will reach the bottom first? So sphere, a pipe, a cylinder, or they'll all reach at the same time. So the key difference, right, each of these has a linear kinetic or a translational kinetic energy and a rotational kinetic energy. The key difference would then be right, the moments of inertia for each of these. So if I break up the equation, 1/2 mv squared plus 1/2 I, my moment of inertia, times the omega, my angular velocity squared. Right, if I break this up again, the only variable that's really going to alter for each of these is the moment of inertia. And the one with the smaller moment of inertia is going to have the smaller portion of rotational kinetic energy, which means it's going to have more linear kinetic energy, right? Since this is all coming from potential energy to begin with, then whichever one has the least amount of rotational kinetic energy will have the most significant, the highest amount of linear kinetic energy, and therefore the highest velocity. Since all of their masses are in fact equal, right? So that takes mass out of the discussion. But anyway, so looking at these choices, once you boil it down to that, it's just a matter of then which one has the lowest moment of inertia. So whether you think it through using the equations or whether you think it through just conceptually, hopefully we all agree that the sphere would have the lowest moment of inertia, right? It would be 2/5 mr squared as opposed to the hollow pipe, which would actually just be 1 mr squared, and the solid cylinder, which would be 1/2, right? So that's the lowest coefficient. Again, conceptually, the reason for that is the solid sphere is going to have the biggest portion of its mass concentrated towards the center or towards the axis of rotation, and that's why it has the lower coefficient for the moment of inertia. But again, in any case, I hope that we're all pretty comfortable with choosing option A there, right? Nothing maybe too tricky to deal with. Okay, so this one's a good setup and a good one to think through here as well. So maybe one of the trickier multiple choice questions in this homework here. You've got a metal ball, or excuse me, a metal bar that's hanging from a hook in the ceiling, and it's suddenly struck with a ball that is covered in glue so that it sticks to the metal hook, right? Then they ask us which of the following is true during the collision. So option A, the angular momentum of the system, the ball and the bar, is conserved about the hook because only gravity is acting on the system. Now, what we're going to see here is the angular momentum is conserved, so that is a true statement. But the rationale is not fully true. Yes, gravity is acting on the system, but it is not the only force acting on the system, right? Gravity is pulling down on the ball, gravity is pulling down on the metal bar, but the metal bar is obviously not accelerating downward, and that's because there is a hook or a tension or whatever you want to consider this force, right, that is holding the bar up as well. So gravity is not the only force acting on the system, and that's really the only reason that we're going to rule out option A. So then option B, the angular momentum of the system is not conserved because the hook exerts a force on the bar. That's not true because angular momentum in this case will be conserved, right? So again, let's break that up a little bit more. Angular momentum is going to be conserved as long as there is no outside torque, as long as there's no net torque. So if I think about this bar, well, this bar is going to rotate around that hook, isn't it? So as the ball sticks to the bar, that bar is then going to rotate upward. So it's going to pivot around that hook. Well, if I think about all of the forces, initially the force of gravity on both the ball and the bar is pulling straight down, right? Whereas the force of the hook is pulling straight up. Each of those forces, all three of those separate forces, are all parallel to the axis of rotation, to the radius, to the lever arm, right about that axis of rotation. All three of those forces are parallel to the lever arm, and therefore they're not going to produce any torque, right? So as I pull down on this bar, I'm not going to cause it to rotate. Same thing with the hook pulling up here. As it's pulling directly upward, it's not going to cause that bar to rotate. So none of those three forces produce any type of outside torque. So my net torque for the system would be 0, and therefore angular momentum will be conserved. So it's not conserved, or to say it's not conserved is not the correct option, right? It will be conserved. So I can go ahead and rule that one out, and then if I look down below, I guess I was thinking there was another option that said that angular momentum was not conserved, but there isn't. So let's just continue to go through these. The angular momentum of the system, the ball and the bar, is conserved about the hook because neither the hook nor gravity exert any torque on the system. And that is going to be true. That's going to be our option. That is correct. Okay, so that's more or less what I just broke down, right? Even though there are forces of gravity and the force of the hook acting, none of those are producing any torque. And since the net torque is 0, the angular momentum before and after the collision would have to be conserved. So then let's look at why options D and E aren't right as well, just to make sure we break this down. Both the angular momentum of the system and its kinetic energy are conserved. Well, in general, that's not true, right? In general, the kinetic energy is not necessarily conserved. And in fact, in this case, as the ball sticks to the bar, wouldn't it be a perfectly inelastic collision? And what is inelastic telling us? Well, inelastic is telling us, right, by definition, if it's inelastic, that kinetic energy is not conserved, right? The kinetic energy before and after the collision are not the same, right? So option D is not right because kinetic energy is not necessarily conserved. And in fact, we could do some mathematics to show that it would not be, but maybe I won't have you worry about that just yet. And then finally, option E, both the linear momentum and the angular momentum of the system, both the ball and the bar, are conserved. So let's talk real briefly. We already know the angular momentum is, so let's talk about the linear momentum for a second. Well, when is linear momentum conserved? The linear momentum would be conserved as long as there's no net force, right? Linear momentum is conserved if the net force equals 0. Well, in this case, as the ball is striking the bar, isn't there a force of gravity acting on the ball that is not being balanced out by anything else, right? So before and then obviously during part of that collision, you're going to have the force of gravity which is acting on this ball and not acting on anything else. So there is going to be a net force, and therefore the linear momentum is not going to be conserved. So that again is why option E is not right, and therefore option C is my best choice. Okay, so question 6, probably the last question I'll get to in this part of the homework here. They give us a string wrapped around the pulley. They give us the lengths and the radius and all that fun stuff to work with. Constant force of 50 newtons is applied to the string, which does not slip. So that tells us as the string is being pulled, it causes the pulley to rotate. If the string unwinds 1.2 meters in 4.9 seconds, and so that kind of jumps out as here's a linear distance, here's a time, and I know that it's starting at rest. So the initial linear velocity would be 0. So that actually gives me 3 pieces of information which might be helpful. But anyway, getting to the heart of this question here. So they're asking us, what is the moment of inertia, right? So we're looking for what's I, what's the moment of inertia? Well, the key relationship that hopefully jumps out here is they give us a force and they give us the radius. And force and radius, obviously, those are measurements that can help me find the torque. And then all of this information, well, obviously, again, this should be hopefully screaming to us kinematics, right? So if that gives us kinematics, that also gives us angular kinematics since we have the radius. So that tells me I can find anything I want kinematically. So the acceleration or the angular acceleration or whatever I may need. And so then if I bring all of this together, well, the net torque, I know the net torque equals the moment of inertia times the angular acceleration. So if I can find the net torque and I can find the angular acceleration, then I've got enough to figure out the moment of inertia. So then that is our task at hand, right? We need to find the net torque on the system, and then we need to find the angular acceleration. So to find the net torque, hopefully not too bad, right? Torque just equals force times the radius. In this case, it's being applied perpendicularly to the pulley, so I don't have to worry about any type of sine of the angle or anything like that. So the force is 50 newtons, and the radius would be, keep in mind I'm going to convert that to meters, so 0.02 meters, right? So 50 times 0.02, and that actually works out very nicely to be just 1 Newton meter, right? So there's my net torque on the system. That is the only force acting. We're assuming there's no appreciable friction, which it says here. So I guess we're not actually assuming that. They tell me that. But anyway, so we've got that. So then kinematics, right? I want to find alpha. Well, probably the thing that I would do, and it doesn't really matter, but I'm going to find my linear, my tangential, I should say, acceleration, and then just convert that to alpha by using my radius, right? So since I know the initial velocity, the displacement, and the time, I'm going to use delta x, so 1.2 equals my initial velocity of 0 times the time of 4.9 plus 1/2 the tangential acceleration and then times the time squared, so 4.9 squared. So then in solving for the tangential acceleration, this actually works out pretty nicely to be about 0.10 meters per second squared. So again, that's the tangential acceleration. But then I do have to convert that to my angular acceleration. So I take advantage of the fact that tangent equals the radius times alpha. So then plugging this in and then ultimately dividing by my radius of 0.02. And I get my alpha, I get my angular acceleration to be about 5, exactly 5 based on this measurement, but 5 radians per second squared. And as soon as I have that piece of information and my net torque, this question becomes pretty easy, right? So the net torque of 1 equals the moment of inertia times the acceleration of 5 radians per second squared. So my moment of inertia then is 0.2 kilograms times meters squared, right? So anyway, this problem is a good one for bringing kind of multiple avenues together to help us find our moment of inertia.